Hi, I'm Andrei from the machine learning team at Zama. In the latest ConcreteML release, we added an API that allows you to fine-tune LLMs on encrypted data using low-rank adaptation. This functionality works by training a small set of fine-tuned weights on the client machine while securely outsourcing heavy computations to remote worker nodes. In this example, we will show how to train Llama to generate Python code that showcases ConcreteML model inference. The original Llama model is aware of scikit-learn syntax, and our small fine-tuning dataset contains example of ConcreteML model usage. This ConcreteML API, in its current form, can prototype the fine-tuning by allowing a data scientist to see the impact of the conversion to FHE computation of the fine-tuning process. Let's dive in. We will use Hugging Face transformers to set up the model and the ConcreteML LoRa trailer class to convert it to fine-tuning with FHE. We will load the model, so here it's Llama 3.2 1 billion parameters using the Hugging Face API, and we will set up the tokenizer. Next, we configure the low-rank adaptation training. The most important parameter here is R, which is the LoRa rank. Here it has the value of 8. This value has a strong impact on the number of fine-tuning weights that are stored on the client side. We then load the dataset. Let's see what the initial model auto-completes for the initialization of a ConcreteML logistic regression model. So this will run the model on this code snippet. It will run it locally, and in this instance we are not yet using the fine-tuning weights. So here we see that although the logistic regression is important from ConcreteML, the parameters to the initialization of this class are those from scikit-learn. The original model does not know about ConcreteML syntax and specific parameters. Now to fine-tune, first step is to convert the model to FHE. So this process takes about 4 minutes for the Llama model on this rather small dataset. So in this step, we are quantizing all the weights and configuring the FHE crypto parameters. In the next step, we will check whether the ConcreteML LoRa trainer can optimize the loss function of the LLM. This step is executed on clear data on the local machine. It is quite fast as it uses the GPU, and it will simulate all the impact that FHE training can have, but on clear data. As we see here, the value of the loss decreases with each epoch. Once the simulation is finished, we check whether the fine-tuned model can predict the correct syntax for creating the ConcreteML logistic regression classifier. What we can see is that the predicted syntax has changed. This new n-bits parameter has been added to the constructor. This is the correct ConcreteML syntax, and it shows that the model has integrated new knowledge. In the final step, we can train on encrypted data. We generate a data set containing a single batch of data, and we will perform the training process using the FHE equals execute parameter. This will perform the fine-tuning on encrypted data. It will not be shown here because it is a quite lengthy process, but ConcreteML ensures that training on encrypted data gives the exact same behavior as the simulation that was shown before. In the next installment of ConcreteML, we will implement a distribution system for the encrypted training tasks. That should bring down the computation cost significantly by distributing computation in a network of GPU-enabled desktop machines.
Thank you for your interest in ConcreteML and its LLM fine-tuning functionalities. If you have any questions, feel free to ask on our Discord server or through the support channels.